Hello everyone. Today we're diving into an important concept in data mining: factor analysis. This powerful statistical method helps us understand complex relationships in our data and reduce dimensionality. In today's video, we'll cover 4 main topics. First, we'll explore the core concepts of factor analysis and what makes it so useful. Then, we'll look at how correlation matrices help us identify relationships between features. After that, we'll dive into feature loadings and learn how to interpret them effectively. Finally, we'll wrap up by understanding variance components, including communality and uniqueness. This comprehensive overview will give you a solid foundation in factor analysis. Let's start with the basics of factor analysis. Factor analysis is a statistical method that helps us explain patterns in our observable data using a smaller set of hidden variables, which we call factors or latent variables. Think of it as finding the underlying structure in your data. It's particularly useful when we want to group similar features together. A great example of this is in petroleum engineering, where we can use factor analysis to study rock permeability. When we perform factor analysis, one of the first things we look at is correlation between variables. Here's a practical rule of thumb. When you see features with correlation coefficients greater than 0.70, that's a strong signal that these features might be combined into a single factor. In our rock dataset example, we found a correlation of 0.82 between perimeter and area, suggesting these features might be represented by a common underlying factor. Now, let's look at how we can represent these relationships mathematically. The factor model shows us how each feature can be expressed in terms of various factors, with factor loadings indicating the strength of these relationships. These factor loadings tell us exactly how much influence each factor has on our observable features. Understanding factor loadings is crucial in factor analysis. When a loading is positive, it means the factor and feature move in the same direction. As one increases, so does the other. Conversely, negative loadings tell us that as the factor increases, the feature decreases. The magnitude of these loadings shows us just how strong these relationships are. In our rock dataset, we can see how features like area, perimeter, shape, and permeability are all connected to underlying factors with varying strengths. Let's talk about variance components. In factor analysis, we break down the total variance into 2 parts: common variance and unique variance. The common variance, also called communality, tells us how much of a feature's variance is explained by all our factors together. We calculate this by summing the squared factor loadings, and it always falls between 0 and 1. The unique variance is what's left over. It might come from measurement error or factors specific to that feature. To wrap up our discussion of factor analysis, let's review the key points. We've learned that factor analysis is a powerful tool for reducing data dimensionality and uncovering hidden patterns. We use correlation analysis to identify potential factors, and factor loadings tell us about the strength and direction of relationships. Understanding variance helps us assess how well our factors explain our data. This technique has wide-ranging applications, from petroleum engineering to general data mining and feature reduction. Thanks for watching. If you enjoyed this video, please like, share, and subscribe for more content on data science and technology. See you next time.